So here are the actual counts that we got. There were 70 blue, 43 red, 29 yellow, 42 green, 71 orange, and 32 brown, for a total of 287. Okay, so obviously this is not perfect to what the distribution should have been. So the question is, how far away is it? Is it far enough away that it's just a little bit of variability in the way that M&Ms are packaged, or is it so far away that we think that maybe this initial distribution isn't very good? So the way that you're going to start is you're going to try to figure out how many M&Ms should I have gotten in each color if this were a perfect bag. So how would we figure that out?
Multiply 0.125 times 287.
Yeah, multiply 287 by 0.125. So let's do that. So that ends up being 35.875. I'm going to label this expected. So these are the number of M&Ms I would have expected to get. And then once you double that to get 71.75, that's how many we should have gotten in a perfect bag of orange and blue. Isn't that pretty amazing? Orange and blue, they're so close to being what it actually should have been. Is that kind of cool? Okay. Now, what I could do is I could calculate the proportion of red and compare it to 0.125 and do a hypothesis test. I could then compare the proportion of brown and do a hypothesis test. Why would I not choose to do 6 different hypothesis tests to look at every color?
It takes forever.
Okay, do you remember talking about that? That the more hypothesis tests you do, the larger an error that you get? You guys okay over there?
Yeah.
Okay, but do you remember talking about that? More hypothesis tests, higher error?
Yeah.
Okay, so that's the problem here, is we don't want to do 6 hypothesis tests. We want to do 1 hypothesis test. So some of you, I believe, have done this before in bio. If you have, keep your mouth shut. Those of you who have not, I want you to come up with a test statistic. So it's not T or Z, but design your own way to figure out how far away is our observed from what we expect it to be. So you're going to do this with the people. How many of you are in AP Bio? Oh, not that many. Okay, so you 3, don't give away my secret. So try to come up with your own test statistic. You're not using a Z or T formula, but your own way to measure how far the observed is away from the expected. So take 4 or 5 minutes with the people next to you. Come up with a formula of some type.
That was just the 12.5 times 287.
Oh, 87.
Because that was how many little pads.
Jack, did you have a question on your quiz?
Oh, I was gonna like show it around.
I don't even want to bother my time because I'm known to be wrong. Like,
There you go.
Wait, so is she saying that you
So
did
a balance
the
is
designs from bio already know it and stuff? So you already know. Yeah, we did this first semester. So I don't remember it that well, but once she like did my stuff.
proportions of red, brown, yellow, red, brown, yellow.
You guys already came up with a test statistic? Okay, well, what's a logical way to start?
Observed minus expected.
Subtract them, right? That would be a good way to start, is to subtract them. So then you got to think about, once I have all those values, what am I going to do with them? Am I going to add them all up? If I do, are there any issues that I might run into? So discuss, don't stare at me, discuss that amongst yourselves.
Okay, so if you take all the differences, you take well, yeah. Yeah. Oh, yes.
And then I take it over all of that.
Like a P value.
to the first standard deviation. Or like a part of the bottom. That's not helpful. My leaf is wide. Yeah. Like it's like swollen. The standard deviation would just be like the difference. Mean difference. Well, I don't know. Could be.
This is a really good try. Okay, it doesn't seem like a whole lot came out of this conversation. So let's see how we did. Talking to this side of the room, we decided that a good idea might be to subtract these two to begin with. So it really doesn't matter the order, but maybe I'm going to take those observed and I'm going to subtract the expected. And then I think the next gut reaction is to add them all up. Now, what difficulty are you going to run into when you just add all those up? Or what issues might arise? Why?
Because some of them are more and some of them are less.
Right, aren't we going to get some positive differences, some negative differences? So then this might sum up to 0 maybe? We've seen that before. What did we do when we had a sum that was 0? Squared it. Okay. But then what we need to also consider is that some of these categories are more frequent. So like orange and blue are more frequent, so their difference should count for more because it's a bigger category. So then what you do is you divide by the expected value. So this is actually the test statistic. Doesn't it kind of make sense? Okay. This is called chi-square. Chi-square, not shy, not chi. Chi-square. Yes, Ariana. I just feel like you're waiting on something. See it? No? Okay. Nothing? Okay. Sorry. I'm sorry to tell you now is where we actually have to take notes. Okay, we just started what's called a chi-square goodness of fit test. AP Bio people, does that sound familiar? Okay. Chi-square goodness of fit test. It tests a claim about the distribution of a categorical variable. Okay, so two things really important. It's an entire distribution of a single variable. So we looked at all the possible colors that M&Ms come in. What you should notice is that this is related to a test for proportion. So like we already talked about, we could have done 6 individual tests based on all the different colors. But we said that's not going to be the most efficient and it's going to compound our error, so we're going to do one test. Here's how they're related. A goodness of fit test is the general case of a one sample z-test. Okay, what I mean by that is that you still have one sample. You still have one question. Your question, though, is more than yes or no. So I'm not just looking at, is the M&M red, yes or no? The question is, what color is the M&M? And then it falls into each of the categories. So chi-square, everything chi-square, that's this whole chapter, chi-square, always categorical data. So chi-square, always for categorical data. Your null and your alternative are going to look a little bit different for a chi-square test. Your null is going to be that the observed distribution is the same as what's claimed. Alternative then would be that the observed distribution is not the same as what's claimed. How do you know if you have evidence for the alternative? Your observed counts are not the same as what you would expect. Now the question is, though, how far away are they? So just because there's a difference in the observed and the expected doesn't mean that the alternative is true. It has to be a fairly large difference. How do you calculate the expected counts? That's what you just did. You take your sample size and you multiply by p. So the proportion, in this case, proportion of red, proportion of blue, etc. Should you round these? No. Just like for mean, you're never going to round the expected values. Chi-square test statistic is the sum of observed minus expected squared divided by expected. Okay, one thing to notice is when you do this formula, you are using counts, not proportions. So on the previous page, for expected, you're going to use these values that we calculated, not these percentages at the top. So just make sure you don't use the percentages. You ready for the good news about this? Is it on the formula sheet? Yes, it definitely is. You do not have to memorize this. Bottom it will even tell you, chi-square test statistic. Right there. You want to know the even better news? This is the only formula for the whole chapter. Every hypothesis test is going to use that test statistic. Right? Do you already see why this is better? Okay, so what does the test statistic measure? It measures how much the observed distribution differs from the hypothesized distribution. By hypothesized, I just mean the expected distribution. Okay, here is where conditions change a little bit. So the normal condition, you're always going to have to check that. The second condition is what changes. So when does the chi-square statistic actually follow the chi-square distribution? So we have a t distribution, a z distribution, chi-square is another one. All of the expected values, so the expected values for every category, have to be at least 5. Just like a t-test, there is degrees of freedom. This one is a little bit harder for students to remember. Degrees of freedom, it'll catch up eventually, so just listen. Degrees of freedom is the number of categories minus 1. So it is not based on the sample size. Okay, next thing, describe the shape, center, and spread of chi-square distributions. Shape, a chi-square distribution is always skewed right. This one's kind of nice. The mean is whatever your degrees of freedom are. So in the M&M case, there's 6 different colors, 5 degrees of freedom. There's always a peak at the degrees of freedom minus 2. Okay, realistically, what of this do I expect you to know? Pretty much that. I want you to know that the chi-square distribution is skewed right. I'm never going to ask you the mean. I'm never going to ask you where the peak is. Okay, how do you calculate p-values? You can use a table. You can use a calculator. Another thing that people really like about chi-square. Chi-square tests are always upper-tailed, no matter what. Okay, we're gonna write down a few more things and then be done. We're going to skip problem 7 because we certainly don't have time for an example. But we're going to talk about the conditions for conducting the test. First condition. What's the first condition always? You have to have a random sample. Does it make sense in this case to say randomized treatments? No. So it's just pretty much always going to be random sample. Second one, you always have to have a large sample. By large sample, I mean that all the expected counts have to be at least 5. Last one, 10% rule. You do not always have to check the 10% rule. Same time as always. If you have a finite population and you're sampling without replacement, then you're going to check the 10% rule. Okay. Real quick, we're going to calculate our test statistic for the M&M example. And then we'll do a full test Wednesday when we come back to these notes. So take out a calculator. Okay, here's what you're going to do. You are going to go to your lists. In the first list, you want all of the observed counts. In list 2, you want all of the expected counts. Okay, you guys ready? We are going to follow this formula exactly. Observed minus expected squared. So we're going to do that first. Observed was in list 1. We're going to subtract list 2 and square it. So that's the observed minus expected squared. We have to divide by the expected, which is list 2. So observed minus expected squared divided by expected. And then you're going to store those in another list, like maybe list 3. Lastly, we want to sum them all up. This is where I can't exactly remember where sum is. Math what? Is it actually? Math? Oh, okay. Well, if you guys have that, I do not have that. No, there's one that just says sum, but it's hidden somewhere illogical. Just says sum. Ah, okay. Found it. Come on, guys. Second list. We're going to go over to math. There's where that sum is. We want to sum up list 3. So that's our test statistic. Now, if we want to find a p-value, always upper tailed. So you're going to go to second distribution, and you have that chi-square CDF that maybe you saw before, maybe you just ignored. You're going to put in the lower bound, which is this number. The upper bound is 1 times 10 to the 99th. And then the degrees of freedom is 5. Very excited to see. Ooh, look at that. What does that mean about our M&Ms? They're good? What do you mean good? We don't have evidence that they're different from what M&M actually claims, or what Mars company actually claims. Okay, good news. If you have a calculator that is newer than this, there's an easier way to do that on the calculator. If you have this calculator, that's your only option. So Wednesday I will show you the other way to do this. We'll go through a whole test, etc.